Hello and welcome to this tutorial on Quality 4.2. So in today's tutorial, we're going to be looking at a technique called predictive maintenance. We're also going to look at some time series data and we'll be working on a package called ARIMA, which is auto-regressive integrated moving average. Uh, Before getting into predictive maintenance, we'll also discuss some of the maintenance techniques that are predominantly used in the industry. So the first kind of maintenance is called maintenance at fixed time intervals. Let us say you're buying a new car, and at the time of delivery, you will be handed over with a service manual. And that service manual will have the time intervals for your maintenance. The first maintenance could be after like 2000 kilometers or 2 months, whichever comes earlier. Similarly, the second service could be after 1 year or 10,000 kilometers and so on. So, this is maintenance at fixed intervals. The second kind of maintenance is called breakdown maintenance. Breakdown maintenance is very expensive. We'll see why it is very expensive. Let's say you have an old car and you've not started your car for 3 months, and all of a sudden you are in a hurry, you are rushing for an exam, and you're trying to start your car, and the engine is not cranking. So now your car is in a breakdown condition. So now you might have to call the mechanic to the place where your car is parked, or you might have to take the car to the service station somehow. And repairing this car, which is in a breakdown condition, is going to be very expensive. That is number one. Number two, you also have an opportunity cost associated. Let's say you missed a flight because of this car breakdown. Let's say you missed an exam because of this car breakdown. So the opportunity cost is going to be very high and it is also very difficult to quantify. So let's say there is a machine, very important machine in a production shop floor, and that machine is in a breakdown condition. So because of this particular machine, the entire production could have issues. So there could be production stoppage. Again, let us say there is 2 hours of production stoppage because of a breakdown machine. So 2 hours of production stoppage is going to have a huge impact on the company's revenue. So therefore, breakdown maintenance is very expensive, and companies try their best to avoid this kind of a situation. The third kind of maintenance is called preventive maintenance. Uh, Again, let's go with a car example. Let us say you are planning a vacation and you want to drive down to a hill station. So before going to a hill station, you might do some, you might take the car to a service center. You will do some checks. You will check the coolant level, engine oil level, and so on. And if required, you will also top up. And then you can clean your brake pads, you can check your tire conditions, and so on. So you proactively take measures to make sure that your machine is good to go for the coming days. So this kind of maintenance is called preventive maintenance. So we saw three techniques so far: maintenance at fixed intervals, breakdown maintenance, preventive maintenance, and the fourth one is predictive maintenance, where we are going to predict whether the machine is going to fail or not with the available data. So let's take a machine at the production shop floor. You will place sensor at different places. Let us say there is one sensor that is going to measure the pressure. One sensor is going to measure temperature. There is another one measuring vertical vibrations. One more is going to measure the horizontal vibrations. So now you have a lot of data. So with all these data, can we predict whether the machine is going to fail or not? Well, you know the answer. This could be modeled as a classification problem. So this kind of models can also be used for doing maintenance activities, and it is called predictive maintenance. But in this tutorial, we are not going to be dealing with a classification problem because you have already done enough of classification problems in other courses. So today we'll be dealing with time series data. We're also going to introduce a technique called ARIMA, which is auto-regressive integrated moving average. Right? We have a data with this. It's called sensor.csv. So this is how the data frame looks like. You have two columns, month and sensor data. Let's see how the data looks like. We'll run this df.describe. You have 105 observations with a mean close to 3,900. Mean value is 613. Max value is crazy, 13,000 or something. Standard deviation is also very high. So now if I print this data type, it is pandas data frame. So we know that this is time series data. So therefore we will read this data in a slightly different fashion. I'm going to use the same pd dot read underscore csv file name index underscore column is equal to month. So remember we had two columns, month and sensor data. I'm going to treat this month column as index. So basically I'm resetting my index to month column. And I'm also telling pandas will treat it as a date. So therefore I'm giving parse underscore dates is equal to true. So if I give squeeze is equal to true, it is again going to convert it to a series. So since we are dealing with time series, we want this data in the form of pandas series, right? So if I press shift tab, we will see squeeze. The default setting of squeeze is false. So since you want it to be a pandas series, I'm just resetting it to be true. Now if I print this and type and print the type, it is going to be pandas series. So let's look at df underscore 10. Right? Here, why I call this time series data? That's because all these data is collected over a fixed time interval. So we have data on first Jan, second, third, fourth, and so on. Similarly, for 105 days, we have collected this sensor data. Right? So this is the difference between the regular cross-sectional data, which you use for regression, classification, and so on, and time series data. For doing a regression or a classification, you don't need to collect data at fixed intervals. But for time series data, you collect data at a regular time interval. You can also see this through plots. If you see the trend is increasing, and then you also have patterns with the data, right? So it is increasing, decreasing, and so on. So you have a pattern. So whenever you have time series data, the first thing you have to do is perform statistical test to understand whether your data is stationary or not. For that, you need to perform Dickey-Fuller test. So stats model, this package, stats models has this package called ActFuller. So for doing this test, hypothesis test, we have this null hypothesis that says your data is non-stationary. The alternate hypothesis tells that the data is stationary. Okay. So how do we do this null? How do we do this hypothesis testing? As usual, it is based on p-value. If p-value is greater than 0.05, we will fail to reject the null hypothesis. If it is less than if it is less than 0.05, we will reject the null hypothesis and say that the data is stationary. So first, we have to see whether data is stationary or not. If it is not stationary, we will do some transformation, we'll do some differencing, we'll make it stationary, and then go ahead with the time series analysis. Right? So first, let us look at the raw data. I'm doing this Fuller test on df underscore 10, which was the original data frame. I'm going to print the p-value. So let me import Fuller and then run the Fuller test. So if you see the p-value, it is more than 0.05. So it is greater than 0.05. We will not reject the null hypothesis. So now there is statistical evidence that the data is non-stationary. We'll see what stationary, we'll see how stationary data looks like shortly. Okay. So let me print this df underscore temp dot head. Let me also So now what I'm going to do is I'm going to shift this data by 12. If I shift this data by 12, what is going to happen is DF underscore 10 starts in 2015, 1872, 1955, and so on. So if I shift by 12, the first 12 rows are going to be NAN, which is a null value. So the same data will start in after 12, 2015, 1872, 1955, and so on. So I'm just shifting the data by 12 units. I'm creating a new column called seasonal underscore diff. And here I'm subtracting df underscore 10. I'm subtracting df underscore 10 dot shift of 12 from df underscore 10. So what will happen? Let's run this and check. As usual, the first 12 rows are going to be NANs. The 13th row is minus 274. That is because you are subtracting 2015. You are subtracting 1741 minus 2015. Right? So 1741 minus 2015 is minus 274. Similarly, 1675 minus 1872. So 1675 minus 1872. So that's why you have minus 274, minus 197, and so on. Right? So let's not run this. So now, if I do an add fuller test on the new column called seasonal diff after dropping the missing values, let's see how the p-value looks like. Well, now the p-value is less than 0.05, which means we can reject the null hypothesis and say that data is stationary. So now, after doing the differencing, we can statistically conclude that the data is stationary. So what is this stationary? Let's plot and see. So now this is the new data. If you remember the previous data, we had trend, seasonality, and so on, which was very evident in the graph. So now if you see, we have mitigated that to a large extent, right? So this is the beauty of differencing. So now you have data that is stationary. Let's build a model. We'll use mean absolute error as a metric to measure the model performance. I'm going to import two plots, ACF and PACF. ACF means autocorrelation function. PACF means partial autocorrelation function, and so on. So let's plot ACF and PACF. So here, the reason for doing this is to identify the number of lag features. So this is the autocorrelation function. Here I see only one feature that lies outside this thick blue region, which is called the critical region. So there is only one feature, lag feature, that is of interest to us. Similarly, the partial autocorrelation function, we have one feature, one lag feature that lies outside the critical region. There is also another feature here, right? So why we are doing this ACF PACF? The reason is if you give ARIMA, you need to give arguments P, D, and Q. So P is the number of lag features from the partial autocorrelation. Well, visually, if you see, you could give one or two, right? So P could be two here, and D is nothing but differencing. Differencing ranges between 0 to 2 generally. And Q is nothing but the autocorrelation function. Visually, if you see, Q will be 1. So 1 lag feature. So the arguments of ARIMA being PDQ, and we could visually say P is equal to 2, Q is equal to 1 from the ACF and PACF plots. So let's import ARIMA. I'm also dividing my data set into train and test. So we have this new data frame. We have this new column called seasonal underscore diff. It starts from 13, it goes up to 85. The reason it starts at 13 is because the first 12 are NAN, and then the test is for the last 20 observations. So if you describe the data, it goes from minus 2041 to 2585. Standard deviation is also high, 806. So now I told that PDQ could be 201 or something of that sort, but I'm randomly giving PDQ as 004, and you can fit this ARIMA model. You could fit, and then you could forecast for the next 20 days. And then if you print the forecast of the next 20 days, this is how it is going to look. Right? So now you can calculate the mean absolute error. You can import it from sklearn.metrics. So now if you look at the mean absolute error for an ARIMA model with PDQ 004, it is 427. Can you get better than this? The answer is yes. Well, we could give other values of PDQ from the PACF ACF plots, but let's do it in a more fancy way. So let us give PDQ as a range from 0 to 5, 0 to 3, 0 to 5, etc. I'll, I'll ignore the warnings. So now I'm creating a function for P in P underscore values, for D in D underscore values, for Q in Q underscore values. I'm just giving the order as PDQ. I'm just giving my model as train, and this is the train data set that comes from this part. Right? The from order comes from here. Then I'm fitting the model, and then I'm predicting the model. That's nothing but model underscore fit or forecast. Length of test is 20. We saw that, and I'm giving 0 because that is where we have predictions. Then comes residuals and so on. So therefore, I'm giving index as 0. We know the matrix is mean absolute error. We are going to calculate mean absolute error for the test data set and predicted data set. The test comes from here, right? So let us print and see. So we have the mean squared error. This is not mean squared error. This is mean absolute error. So the mean absolute error for different values of PDQ are printed here. So we had a benchmark of 427. Can we get better than this? Let us find out. Do we have MAE less than 427? Oh yes, 426, 400, oh 389. So looking at this, we see 389 seems to be the best. Well, the answer is yes, PDQ. So P being 2, uh, D being 0, and Q being 1 gives us the best forecast with the mean absolute error of 389. So this is one way of doing time series forecasting. So there is another method called ARIMAX, where you are dealing with multivariate data. Then you have SARIMA, SARIMA, where you are specifically uh, dealing with seasonality. And then the other interesting forecasting techniques are Profit, Facebook Profit. So that's another very important tool in time series forecasting. So this is just an overview about time series forecasting, right? Um, with this, uh, start exploring more time series models. That's going to be of great help in the industry. So let's conclude this lecture here.